We talk a lot, about creating models.
All the time.
Yeah, simulations, digital twins, all these climate projections we see, even things like large language
Right.
models. We're
Yeah.
always trying to capture some little sliver of reality, distill it, and then, make it predictable, make it
Mm.
manageable and useful for us.
But what if that's the wrong way to look at it?
How do you mean?
What if the biggest hurdle in modeling isn't really the complexity of the thing we're modeling? What if the real barrier to success is, well, the sheer volume of information?
Okay, that's interesting.
And what if the only path to real knowledge demands a, a deliberate, almost radical act of chosen ignorance?
That is the core challenge we are tackling today. And I have to say, it's a profoundly counterintuitive idea.
It really is.
We're doing a deep dive into source material that I think fundamentally questions our confidence in prediction and simulation.
And we're pulling this from the foundational work of Stanislav Lem, his 1964 masterwork Summa Technologiae.
And what I find so compelling about this text is that it predates everything we think of as modern. It predates modern AI, complex computing, the internet.
Oh, absolutely.
But he was analyzing cybernetics back then, and his conclusions feel, frankly, terrifyingly current.
They really do. Specifically, we're diving into Chapter 5, Prolegomena to Omnipotence, and we're going to focus on this really densely packed section called Models and Reality.
And this is not just a discussion about, how fast our processors are or how much data we can cram onto a hard drive.
No, it goes so much deeper. It's really about the nature of information itself. It's about the whole process of scientific prediction and this profound, almost mystical question,
Which is?
whether the entire universe is just a highly complex but, ultimately solvable equation, just waiting for the right decryption key.
Okay, let's unpack this. So our mission for you, the learner, is pretty ambitious today. We're going to spend the next half hour trying to understand why successful modeling actually demands that we ignore most of the information out there.
Why we have to choose what to forget.
Exactly. And why trying to replicate the human mind is inherently paradoxical. Why it forces us to build models that are structurally, totally alien to the original thing.
And maybe the most mind-bending part of all,
Go on.
whether a scientific theory can literally contain more knowledge than was ever deliberately put into it.
Right. We're going straight to the epistemological limits of what we can even know through imitation.
So let's start with Lem's, his fundamental definition of what modeling even is.
Okay.
He says modeling is an imitation of nature, but it's an imitation that is, by its very nature, incomplete. It's an act that only accounts for a few of nature's properties.
And the immediate question that pops in my head is, why only a few?
Yeah.
Is that just because of our technological shortcomings? Or maybe we just don't have enough data? I mean, in the age of big data, surely we can model everything.
And Lem argues very emphatically that that's not the primary reason.
No.
He completely flips the narrative. The need for simplification, he says, isn't rooted in our incompetence. It's actually a vital self-preservation mechanism.
Self-preservation.
We must protect ourselves from an excess of information.
An excess of information.
And that excess, paradoxically, doesn't lead to more clarity. It leads to information overload and ultimately to inaccessibility.
That is a fascinating and, a radical concept. We always assume that more information equals more understanding.
Right. Maximal data, maximal clarity.
But you're telling me that information can be so present, so massive, that it just becomes unusable or unreadable. The noise just completely drowns out the signal.
Precisely. I mean, think about it. If we try to account for every single property of a complex system,
Like what?
the quantum noise, the molecular flutter, every single environmental interaction, the heat fluctuations. If you try to build a model with all of that, it becomes so complex that it's useless for generalization or for prediction.
It just becomes a replica.
It becomes a replica, and as we're about to discuss, a replica explains absolutely nothing.
Okay, so let's ground this. Can you give me a concrete example from the source material? How can information be physically there in a system, but completely inaccessible to us, even to the system itself?
Lem uses this really potent example of a painter.
Okay.
A painter creates a masterpiece. Now, by any metric of causality, all the necessary information about how they did that,
The brushstrokes, the color choices.
the precise sequence of firing neurons, the micro adjustments of their muscle fibers, the really complex aesthetic processing happening in their brain, All of that resides physically within their brain, right?
Sure, the brain is the material substrate of the art. It has to be in there somewhere.
But the painter themselves doesn't know. If you ask them, hey, tell me the exact subneural algorithm you used to decide on that shade of blue, they can't answer.
No, of course not. They can talk about technique or maybe, it just felt right, but they can't describe the physical process.
Exactly. And even if we had some impossible instrument that could scan that brain at a molecular level, capturing, the 10 to the 28th power or whatever individual data points, we would just be overwhelmed.
So it's a sea of data.
A sea of data. That raw, impossibly detailed data set is informationally present. It's embedded in the neural architecture, but it is functionally inaccessible. You can't process it into knowledge.
So that forces us then. When we model something like creativity or cognition, we have no choice but to simplify. We have to abstract.
And this leads us right to the core paradox of fidelity versus utility.
Okay.
To create a successful and insightful model, we must simplify. We have to choose what information to deliberately throw away. If we go for maximum fidelity,
We lose all the utility.
lose all utility, correct. The text draws this really stark contrast. Think about a machine that's built to write a modest painting. Even if the output is, crude or basic, imperfect, that machine tells us infinitely more about the material basis of painting, about the underlying brain processes, than a perfect but totally mute model of the artist.
And that perfect mute model would be, as you mentioned, something like the artist's identical twin.
Exactly.
The twin is a perfect reproduction of the initial conditions, but it gives you zero explanatory power. It just is. It doesn't tell you how the process works.
Yeah.
But the crude machine, it demonstrates the mechanism. It shines a light on what the source calls the material, that is, brain basis of painting.
This separation is absolutely vital. The whole point of modeling isn't to duplicate reality. It's to understand the rules that govern reality.
So the practice itself assumes we're choosing certain variables and intentionally rejecting others.
Yes, and if we don't reject that information, we get a perfect copy, but we sacrifice all the knowledge.
And it's that intentional rejection, that necessary simplification that guarantees divergence.
Guarantees.
Because if the processes in the model and the original were a perfect match, they'd be identical and therefore useless as a model. But since they have to diverge, because we simplified, the model's path is fundamentally different from the original's actual messy development.
And this divergence, this necessary split, is driven by three essential factors, according to Lem's analysis.
Okay, I think we should spend some time on these because they really set the stage for the rest of this whole deep dive.
Absolutely. The first factor is, well, it's the most obvious one. It's the inherent simplification of the model compared to the original.
That's the part we just talked about, the deliberate stripping away of variables to protect ourselves from that information overload.
Exactly. If the real thing has a million interacting parts, and we choose to model just 10 of them, we've already introduced a massive potential for divergence.
Okay, that makes sense. We trade fidelity for explanatory power.
Oh.
What's the second factor? You said it was more complex. Something about properties alien to the original.
Yes, and this is where the philosophical challenge really kicks in. The second factor involves properties that belong to the model but are completely alien to the original.
Alien to the original.
The term the source uses is chuste originalu. These are structural differences we introduce simply because our artificial medium, be it an electrical circuit, a computer program, a mathematical equation, it just doesn't behave like the biological or physical system we're trying to imitate.
So if we use a computer chip to model a neuron, the chip itself has properties like heat dissipation, a fixed architecture, binary logic that the biological neuron just doesn't have in the same way.
Exactly.
We're building an alien structure to simulate a native function.
Precisely.
Yeah.
We are forced to build in components that do not exist in the reality we're modeling simply because our engineering materials demand it. This is divergence driven by our tools, not by the original's complexity.
Okay, so that's two. And the third factor.
That would be the inherent uncertainty or indeterminacy of the original phenomenon itself. Even if we could perfectly capture and model a system at one single moment in time, the underlying physics of reality, whether it's quantum indeterminacy or complex nonlinear dynamics or just simple environmental noise, means that the original is inherently unpredictable in its exact path forward.
So the original system, the real apple, the real brain, the real climate, it's always a little fuzzy. It's always prone to a degree of genuine randomness.
It is. We can never truly know its exact path, which means our model, no matter how detailed, is always starting from a flawed or incomplete foundation of knowledge about where the original is actually going to go.
So, wow, modeling isn't just hard because we lack computing power or data.
Mm,
It's fundamentally philosophically flawed from the get-go because we must simplify, which is factor one.
right.
That simplification automatically introduces these external alien elements, factor two,
Mm-hmm.
and the reality we're chasing is inherently non-deterministic anyway, which is factor three.
Exactly. Divergence is guaranteed. And this sets really the inescapable stage for the ultimate modeling challenge, the human mind.
I think we can all agree that modeling the human brain, or really any highly complex cognitive system, is the absolute pinnacle of this challenge.
It is.
When we move from modeling something simple, like a projectile's trajectory, to modeling thought itself, those three factors of divergence we just talked about, they become acute, even contradictory.
Absolutely. When a cyberneticist tries to imitate mental processes using a non-biological medium, say an electronic scheme made of wires and transistors and logic gate, those structural differences, those alien properties, they start to manifest physically in the machine.
Okay, let's trace this out. Let's start with the functional components. If I'm a cyberneticist building an electronic brain, what's the first huge structural difference I'm going to run into?
The first major hurdle is the memory problem. And this illustrates factor two beautifully.
The alien properties.
Yes. You look at the original, the living brain, it's a holistic structure. There's no separate centralized memory reservoir labeled data storage. Memory is universal. It's scattered throughout the entire neural network. It's inseparable from the processing structure. The network is the memory.
And that distributed holistic storage is what makes the brain so robust, so resilient to damage, but it's incredibly difficult to replicate artificially.
It is. The typical artificial model, the electronic scheme, it just lacks that universal capability. You can't just spread the memory across the whole circuit in the same way, not without massive inefficiency.
So what does the cyberneticist have to do?
They have to supplement their electronic brain with specialized, separate memory reservoirs.
Like what?
In those days, large blocks of magnetic tape. In modern terms, you'd think of separate solid-state drives or, dedicated blocks of RAM.
So you're introducing a specialized, centralized memory unit, completely detached from the core processing unit.
And that is a perfect physical example of factor two. You are introducing properties alien to the original. The model now has a separate place for memory.
A physical box, a component the real brain fundamentally lacks, because in the brain, the processing is the storage.
That structural divergence is immense.
It's like trying to model a plant that grows its roots, stems, and leaves all at once from the same cellular structure, but your model requires three separate pre-made components, a root unit, a stem unit, and a leaf unit that you have to bolt together.
Great analogy. The function might be simulated, but the architecture is fundamentally radically different.
Okay, so that's memory. What's next?
That leads us to the second, and I think even more philosophically challenging problem. This relates to factor three, the inherent indeterminacy of the original.
So free will, unpredictability.
Something like that. The real brain exhibits a degree of, let's call it randomness of behavior, and inherent fuzziness in its actions.
But the electronic scheme, the computer model, is typically deterministic.
It's designed to be. Unless you program it otherwise, you give it the same initial state, the same input, the machine is built to be completely predictable. It must give the same output every single time.
So if your machine is perfectly deterministic, it can't possibly model the unpredictable behavior of the human mind.
It can't. So to simulate that unpredictability, the cyberneticist has to deliberately build in what Lem calls an accidentality generator.
An accidentality generator.
Yes, a device for generating accidentalness.
Yeah.
This thing uses, pre-provided random number tables or chaotic physical inputs, something designed to inject randomly chosen signals deep into the circuit.
So let me get this straight.
Yeah.
We build a machine whose entire virtue is its predictability and its logical calculation. And then we have to deliberately install a specialized component whose only purpose is to make the machine less predictable, just so it can mimic the observed fuzziness of a real brain.
That is a definition of a paradox in engineering. Yes.
Wow.
It's a necessary workaround that actually highlights this deeply cynical philosophical assumption, which is that we are essentially modeling free will as just structured, engineered randomness.
And Lem saw this coming.
He did, and he even acknowledged this fascinating counterpoint. He noted that even back then, in the 60s, so-called modern electronic schemes did exhibit their own non-deterministic randomness, just from, electrical process misalignment, undeterminable delays, data transmission errors, little glitches.
That's ironic. So sometimes the imperfection of the machine accidentally achieved the necessary unpredictability.
It did. But whether that randomness is accidental or engineered, the point remains the same. The model now has this specific, localized, specialized device, the accidentality generator, which the biological brain does not have as a distinct anatomical feature.
Okay, so this brings us to what you called the core structural trade-off. This feels like the big aha moment of this whole deep dive.
It really is. So after adding these specialized separate features, the separate memory reservoir and the randomness injector, the similarity of the output parameters has increased.
Meaning it behaves more like the real brain.
Yes. The input-output dynamics are closer. We might even call the model a success.
What?
But simultaneously, the similarity of the entire structure decreases dramatically.
Ghastly.
The model now has these discrete foreign components, the generator, the separate memory, that the real brain fundamentally lacks. And if you wanted to go further, say, trying to account for the variable excitability of neurons.
Which the real brain does through complex biochemistry.
Exactly. To model that, you'd have to equip every equivalent switching element in your circuit with yet another special, dedicated electrical scheme.
The complexity just explodes, and the structural divergence becomes astronomical. We've created this complex Rube Goldberg-like contraption that gives us the right output but looks nothing like the elegant, holistic, living machine it's trying to imitate.
And this leads us to the ultimate simplification principle. The modeler, to make their model useful, has to perform what Lem calls preliminary selection.
They have to choose what matters.
And the variables that are present in the model but absent in the original phenomenon are simply dismissed. They're called non-essential. They're just a byproduct of the medium we chose.
That's the ultimate rationalization, isn't it? We put in an accidentality generator because we need random output, and when we realize the brain doesn't have one, we just say, oh, well, the generator is just non-essential structural noise.
And that judgment of essential versus non-essential is entirely dependent on your goal. Lem borrows this great analogy from Ashby.
What's that?
For a person on a regular telephone call, the crackling on the line is just noise. It's something to be ignored. It's non-essential to the conversation.
But for the communications engineer who's testing that line, who cares about the fidelity of the connection?
That very same crackling is critical information. It has to be analyzed and eliminated.
The input is identical, but the informational content, its value, is radically different based entirely on the goal of the observer.
That's it. The moment we define our goal for the model, I want to model political decision-making, for example. We inherently select what is essential, and we guarantee that the model will be structurally alien to the original in every other aspect.
Which means that while digital modeling can be useful when the variables are small,
as complexity increases, the method just quickly reaches a ceiling, a limit of applicability, and that forces us to seek an alternative approach to getting knowledge altogether.
that is the perfect segue, because these inherent difficulties of imitation, this guaranteed divergence between structure and behavior, it leads us to a kind of philosophical dead end.
It does.
If your goal is perfect imitation, the ultimate model is just useless.
It leads to what Lem calls the reductio ad absurdum of imitation practice. The most economical model of an apple is just another apple.
The best model of the cosmos is another cosmos.
Exactly. If you want a perfect working model of a man, you have to recreate the man, which achieves nothing new. Imitation, when you push it to its logical extreme, becomes utterly useless as a way of acquiring knowledge.
So we arrive at this pivotal, profound question that just flips our entire understanding of knowledge on its head. Is there something that, while not being a faithful repetition, not a model of a phenomenon, actually contains more information than the phenomenon itself?
Something that transcends that need for structural fidelity.
Yes. Is there such a thing?
And Lem's answer is a powerful, resounding yes.
Yeah, it is.
Scientific theory.
A theory operates on a completely different plane from a physical model. A model tries to mimic all the specifics.
Whereas a theory covers an entire class of phenomena. It speaks about the universal, the general properties of everything in that class, and it deliberately dismisses the specific details that are non-essential for its goal.
Right, and that's its strength. If we're trying to understand gravitation, the theory of general relativity doesn't need to know the color of the apple, or its temperature, or its chemical composition.
Those specifics, while obviously integral to the apple's existence, are irrelevant to the core mechanism of gravitational interaction. A theory is an abstraction that filters for universal rules, unlike a physical model, which just gets bogged down in all that local, overwhelming noise.
So the theory is a superior form of information storage. It's condensed, it's abstract, it's relational. But this introduces a massive new challenge, a huge paradox of predictive power.
Yes, what the source calls the information balance paradox. Or you could write it as 6 docs right arrow x plus n dollar.
Explain that. What is 6 right arrow x plus n dollar?
It's the idea that a scientific theory doesn't just contain the information we put into it, the x, our initial observational data.
Okay.
It can actually yield additional information represented by that plus n, information that was not explicitly known or observed beforehand.
How is that even possible? I mean, if the universe is a closed system of information, bound by energy conservation and all that, this shouldn't be possible in the realm of knowledge. You can't just get new knowledge from old inputs.
Logically, it feels like it should be impossible.
Right. But Lem argues, and history confirms, that scientific deduction allows us to extract this 6 docs plus n dollar. We get new, previously unknown phenomena out of it.
The source gives these powerful foundational examples from theoretical physics to back this up.
Such as?
Take the quantum theory of the physical vacuum. When it was first constructed, it was based on established facts, known observations. But when physicists started analyzing the structure of the theory itself,
They found things they weren't looking for.
they found they could predict a whole range of phenomena that were entirely unknown when the theory was first put together.
And this wasn't just, slightly better calculations. This was entirely new physics, just waiting to be discovered inside the math.
Exactly. This included specific, verifiable results about beta decay, which is a type of radioactive interaction. But it also extended into predictions about things like superfluidity.
The bizarre zero viscosity state of liquid helium.
Right. And even general principles that are essential to solid-state theory, which is all about how matter behaves in solids.
So these were phenomena that were deduced first, not observed first. That information was latent. It was hidden within the logical and relational structure of the theory itself, just waiting for the right deductive transformation.
That is a fantastic way to put it. It's like you buy a key based on one lock you've seen, but then you realize that the key, because of its specific, intricate structure, also happens to open a dozen other locks you never even knew existed.
So what's the source of this mysterious extra information, this powerful plus n that elevates theory above just processing data?
Lem argues that this extra information appears because changes in the world are, generally speaking, mutually interconnected.
Things are not isolated.
Not at all. They exist in this giant interwoven web of causality and rule sets.
I see. We deduce one fundamental thing, like a core physical law about space and time, and that deduction, because the world's all interconnected, it pulls along another necessary consequence with it.
Yes, and that reveals hidden relationships that were always there in reality, but they weren't visible in our initial limited observational input.
So the theory isn't creating new reality. It's revealing the vast implications of the limited reality we initially showed it.
It's a structure that reviews itself. It's like discovering the grammar and vocabulary of an alien language. You might only start with 3 example sentences, but once you figure out the deep grammatical structure, you can deductively write thousands of new, logically sound sentences that you've never seen or heard before.
The interconnected rules of the grammar create new, verifiable information.
Precisely.
Which then leads to this really profound philosophical implication, one that challenges our whole understanding of the mind itself.
Yes.
If a theory can do this, does that mean that a sufficiently complex system, like our brain, can create additional information compared to what it started with, and do so without new external information coming in?
That's the critical question. If the brain is just a processor, it should only be able to output what it takes in, maybe reconfigured. But if its internal deduction engine can capture and use that interconnected structure of reality, encoded in the rules it follows,
then thinking itself becomes a creative act.
Right.
It generates new verifiable structural information entirely internally.
We become information creators, not just information processors.
And this inherent ability of a theory to generate unexpected, true results is precisely what modern information theory, surprisingly, has a really hard time resolving or even measuring.
We have to dive into why contemporary information theory, sort of falls short here, why it can't really explain this 6-docs right arrow x plus NA paradox.
Okay.
Information theory, as it stood then, and largely still does now, defines its terms based on probability.
This is what's called selective information, right? The less probable a signal is, the more information it contains. It's basically a measure of surprise.
Exactly. But selective information is profoundly indifferent to two things that are absolutely essential for scientific theory: truth and value.
So we need to focus not just on the surprise factor, but on the structural integrity of the message, whether it actually maps to reality.
Yes, and Lem's stark comparison here really drives this point home.
Let's hear it.
Imagine a message arrives that says, stars consist of Swiss cheese. According to selective information theory, the quantity of information in that message is enormous.
Why?
Because the probability of receiving that precise signal compared to the infinite other things stars could be made of, rock, plasma, pudding, you name it, is extremely low. So it contains massive selective information. It's maximally surprising.
But because it's completely false, it contains zero structural information.
Precisely. Structural information is about the correspondence of the information to a certain reality or phenomenon, its truth value, its relationship to the known laws of physics. The cheese star's message is high on surprise, zero on truth.
And it's this indifference to value that makes traditional information theory incapable of assessing the real power of a scientific theory.
Right. You might get two outcomes from a theory, one true, one false, but both might score the same on a selective information test just because they're equally surprising.
Lem gives an example of this too, right?
He does. He goes back to the quantum theory of the physical vacuum. We mentioned that it correctly deduced specific facts about beta decay. That's structurally true, immensely valuable. But the very same theoretical framework also suggested, in some calculations, that the charge of the electron is infinitely large, which is physically false.
And a physicist would instantly use experimental data, or even just intuition, to reject the second finding and embrace the first.
Of course, but traditional information theory remains equally indifferent to that choice. It can't account for the value of the discovery in terms of how it structures our understanding of reality.
And there's another problem too, isn't there? The interconnectedness of knowledge.
It's a huge problem for measurement. No theory exists sovereignly. Every single concept, every formula, it partially derives from others. It combines with them in this inseparable historical and logical web.
We talked about this. You can't separate Kempsey and Tutanua from the centuries of physics that defined what energy, mass, and the speed of light even are.
All of that information just pours into it from this enormous quantity of other formulas and established theories. We can measure the length of the inscription EMC22, but we can't measure its informational density because that density relies on the entire contextual web of physics that supports it.
So this difficulty leads us away from practical cybernetics and straight into the ultimate philosophical question of reality structure, which Lem frames in this wonderful, almost funny way. The shoelace joke.
The shoelace joke, yes. It's this radical thought experiment. The suggestion that all the accumulated knowledge of science, the entire total truth about the universe, all its possibilities and all its prohibitions, could potentially be read from a simple piece of matter.
Like an old shoelace soul lying on the ground.
Or a single hydrogen atom.
It's a deliberately provocative image. It suggests that information isn't added to matter over time through complex interactions, but that it's already fully and structurally inscribed within it, just waiting for the right kind of intelligence to decode it.
He clarifies this idea. He calls it a tautological ontology, using a really simple mathematical analogy, one that every student runs into.
What's that?
The basic equation, $4 plus x equals 7, 2 says.
Okay. The solution, x by 3 through t3 dollars, is already in the equation. It's hidden from the student, but it appears as soon as you perform an elementary transformation. You subtract 4 from both sides.
The information is present, it just requires processing, or in this case, decryption.
And the ultimate philosophical question this raises is nature the same?
Is the entire code the possibility of creating stars and sewing machines and roses and silkworms and even systems 1 trillion times more spiritual than man? Is all of that already inscribed in the most basic brick of nature, like a simple hydrogen atom?
If that were true, Then by analyzing the physical properties of the most basic component, we could deductively derive all possibilities, from the modest ability to make 100 chemical elements right up to creating unimaginable consciousness.
The complex is simply the logical permutation of the simple, once you know the rules of transformation.
And, just as importantly, we could deductively derive all the impossibilities, the prohibitions that are coded into the material.
Things that are just logically inconsistent with the code, like sweet table salt, or stars with diameters of a quadrillion miles. They simply cannot be realized within the fundamental code of reality because the code itself prohibits them.
This completely flips the role of the scientist. We're not discoverers, in the traditional sense, finding new stuff that wasn't there before.
We are decoders. We are cryptographers. We're the incapable student trying to solve the equation of the universe. The information is fully contained within the material code, but we haven't yet acquired the necessary transformational rules, the mathematical, the physical, the philosophical tools to extract it all.
And that, in its most radical form, is what Lem defines as a tautological ontology.
The philosophical view that the essence of all things, all potential, all prohibition, is already present in matter, just waiting for decryption by a sufficiently complex intelligence. Our knowledge isn't invention, it's extraction.
This has truly been a deep dive into the limits and the capabilities of human knowledge.
It's a lot to take in.
It really is. We started with this practical, necessary need to simplify, the idea that we have to ignore most of nature just to model one tiny useful part of it.
Then we move through the paradoxes of building an artificial mind, showing that structural fidelity is basically impossible if utility is your goal.
Forcing us to build models that are fundamentally alien to the original.
And then we arrived at this astonishing revelation that our most successful tool, scientific theory, transcends these limits. It taps into the fundamental structural interconnectedness of the world,
Allowing us to extract more information than we ever thought we put in. That six-dogly right arrow X plus NATO monodox.
Right.
And for you, the learner, I think understanding the limits of modeling is so crucial for rapidly acquiring knowledge. Sometimes trying to perfectly imitate or memorize a complex system is the slowest, most inefficient way to understand it.
Absolutely.
Abstracting it into a theory, which looks nothing like the original phenomenon, an equation looks nothing like a rose, that can be the shortest, most powerful path to mastering the underlying rules of reality.
So what does this all mean for the ultimate project of science and technology, for our future development?
Well, if this tautological ontology holds, if all possibilities and prohibitions are indeed coded into matter, then our entire endeavor of science, of technology, even philosophy, it's not really invention, not creation in the purest sense.
It's purely one of decryption, finding the hidden solution.
And that raises one final provocative thought for you to consider.
Does this mean that the future creation of those systems a trillion times more spiritual than man, something we talk about as a future technological feat,
Is not an invention at all. Is it merely the inevitable hidden solution to a cosmic equation that we have just begun to read?
if the answer is already inscribed in the matter all around us, then our genius lies only in our ability to finally apply the transformation rule and read the code.